is we have to schedule a midterm exam at some point. We are roughly past the midpoint of the semester. So I'm thinking sometime in early April. April 3rd is a Wednesday. I am actually not going to have a class on that day because I was going to be away. So I figured we could actually have the midterm on that day instead. Okay, that still gives all of you 2-3 weeks to prepare for it. So I'm going to say we'll do it in early April. Does anyone have any issues with that? I think that's probably quite late anyway because the semester will end 3 weeks later. So you can't delay it a whole lot more. I mean, you can do it earlier, but I don't want to keep pushing it back. Okay, so it's early April. Okay, I'm going to announce the midterm exam on the class mailing list, but I just want to get some feedback. That's fine. Yes?
If we had it then, do you think that you'll give us feedback before the final?
Absolutely. Otherwise, I think, yeah, we'll get it back, the graded things back to you in a week after the midterm. Okay? So let's plan on midterm on April 3rd. All right? I will put up a note on the on Moodle and also send out an email about this. Okay? There's a homework out as a reminder. I believe it's due this week. So keep an eye on similar announcements because we will probably hand out a lab soon, and I would like it to be due before the midterm if possible. We'll see whether the timing works because there is a week of spring break coming up. Okay, so I'm going to see what's the best option to have it be due after or before. I don't want the lab and the midterm to get mixed up. I want you to focus on only one thing at a time. So I'm going to look at what's the best option there. Okay. All right. So let's continue our discussion. Last time we were talking about leader election. I presented a set of algorithms to do leader election. Then we talked about distributed mutual exclusion. This is the problem of using locks in a set of processes that are running on different machines. Okay, so you cannot actually make the same assumptions that you make when you have a single-threaded, not single-threaded, a multi-threaded application with lots of threads in them that are sharing a data structure. So we looked at how do you implement locks. We looked at a very simple centralized approach where you use leader election, you elect a leader or a coordinator, lock coordinator, and what the lock coordinator does is simply process requests for locks that are coming in FIFO order and grant lock. And the problem with the approach was that if the coordinator crashes, then you are not going to know what the state of the lock was before the crash. Okay, so then we looked at a distributed algorithm, in particular two that we looked at. The second one was really based on using the notion of a timestamp. This is the Rickert and Agarwal algorithm. It uses event ordering and timestamp, and basically, so what it does is very straightforward. Every request that is being sent out, every request for a lock acquire is sent to all processes. And you put Lamport, you use Lamport's clock and you attach a timestamp to that process. If no other process in the system wants the lock, then you get the lock. So there is no contention for the lock, so the lock is acquired. On the other hand, if there are at least two processes that both want to acquire the lock, there is going to be contention. And what we will use is we'll use the notion of Lamport's clock to figure out which process should get the lock. There has to be a way to decide which process should get it if there is contention. And what we will do is we'll simply use Lamport's clock to figure out which lock request happened before the other one. And the one that came in for first, as per the happened before relationship, is the one that is going to get the lock. Okay, so if you receive a request, so if you receive a request and there is no contention, then you just say, fine, go ahead, acquire the lock. If the process already holds the lock, okay, then there is no contention, the lock has been granted, then you just queue up the request, wait for the lock to be released, and then you reply. And if there is contention, both processes want to acquire the lock, then you compare the timestamp of process J's request for the lock with the timestamp of process K's request, and you basically decide which of those is going to get the lock, okay, based on the timestamp order. And note here that as per Lamport's clock, we said comparing timestamps doesn't tell us which event happened before which other event. If you want that property, you have to use Lamport's clock. Right? Only in one scenario does Lamport's clocks allow you to actually compare timestamps and figure out which event happened before which event. And that scenario is one where every request is broadcast to every other request. In this case, since all processes are receiving all requests and acknowledgements are going back, you can actually compare the clock values and figure something out. Okay? So, because here every request for a lock is actually being sent to all processes, you can still do it. Okay? If that was being only sent to some select group of processes, you would have to use vector clocks, but the same algorithm. Okay? Now the question is, so this is a distributed approach for implementing a lock.
So here in this case, the TS and TK can't be like concurrent or something. It's like in the case where we can't say whether one is strictly less or strictly.
Yes. The question is, if TS and TK, if they are concurrent, then you cannot say anything. Right? In this case, because every message is actually sent to every other process. Okay? Though the events are not going to be concurrent. Concurrent events only occur when the processes are not communicating. Okay? There is no message to order them. Okay? Here every message is actually going to go to every process, so that scenario will not arise at all. Okay? Yes, the scenario could arise, but because of the special way in which the algorithm works, which is broadcast, that scenario doesn't occur. Okay? But yes, if that did occur, you couldn't have said that. Okay? Any other questions here? Okay, so here is some properties of the decentralized approach. First of all, it is distributed. You don't need any centralized coordinator. Okay? That's a good thing. But as you can imagine, there is a problem with the approach, which is now rather than a single point of failure in the centralized approach, there are n points of failure. Okay? If any process crashes, not just the coordinator, that process is not going to send a reply message which is saying go ahead. Okay, and you can only grab the lock if every other process says it doesn't need it and you should go ahead. Okay? So if any process fails to reply, you are going to block waiting for that reply, and you cannot actually acquire the lock. Right? So this is a rare scenario where making the algorithm distributed has resulted in worse failure properties than a centralized approach. Typically in a centralized approach, you have a single point of failure. So you try to make a approach distributed that gives better properties, both in terms of scalability and reliability. Here is a scenario where the algorithm is built such that it is distributed, but not hearing from a process because it has crashed actually causes other processes to block and avoid progress in the system. Okay, so endpoints of failure. Yes, since all processes are all involved in all decisions, either a failure of the process or making it overloaded or having it overloaded can either be a bottleneck or can cause a deadlock. Okay, so these are some things to keep in mind. So all this says is it doesn't mean that just making something distributed solves your problem. You have to think carefully about what properties your distributed algorithm has, and can you actually get better results rather than worse results. Okay. Any questions on this? Okay. Last technique we will look at is for distributed locks is token ring. Okay. This is derived directly from token ring networking protocols that were designed, I think, 20 years or 2 decades ago. So what happens in this case is all processes that are participating in this lock process are going to be numbered 0 through n, and they are arranged in a sequence or logical ring, as is shown in that figure to the right. Okay. So what happens is there is a special packet called a token, okay, that's going to arbitrate access to the critical section or give mutual exclusive access. Okay. So if you need to acquire a lock, all you have to wait for the token to come to you. When the token comes to you, there's only one token in the system, and the process that holds the token at any given point in time is assumed to have mutually exclusive access to whatever lock it is trying to acquire. Okay, so there's one token per lock. And so all you have to do is wait for the token to arrive. The token just circulates. Okay, so maybe it starts with process 0. If it doesn't need the lock or it's done with the lock, it just sends it on to 1. If one needs to enter the critical section, it will hold the token, okay, and then do whatever it needs to do, and then send the token ahead. And if it doesn't need it at this point on, it just sends it for to the next process. Okay, so token will keep circulating, and since there is only one token, the process that holds the token is guaranteed that no other process will be doing anything with respect to the critical section. Because the rule is you need to hold a token in order to get mutually exclusive access to whatever data structure you're trying to access or the critical section you wish to enter. Okay? So that's basically a simple approach. And this, as I was saying, this is inspired directly from LAN protocol, token ring LAN protocol that you may have studied in a networking class, for instance. Okay, so back in the days when LAN were actually just beginning to emerge as a popular way to network machines, there are two competing protocols, Ethernet and token ring. Okay? Ethernet essentially assumed that the medium was shared, and each node essentially could transmit at any time, and if some other node was also transmitting, your packets would collide and you would have to detect that and back off and all of that. So it was built around this approach of using a shared medium but distributed way to access a shared medium. Token ring was built around a different philosophy which said that there will be some entity, in this case the token, that will arbitrate who gets to transmit packets. You don't want multiple nodes transmitting at the same time. Right? So the token there was basically used to get a lock on the network so that this node could transmit and no other node was transmitting at the same time. Okay, you can use the same idea to implement locking for any other reason, okay, rather than just saying, do I have a right to transmit when nobody else is transmitting? Okay? Yes.
Is there ever any reason to limit the speed at which you pass the token if no one's interested?
Is there a reason to limit the speed?
Yeah, like instead of immediately passing it, if you're not interested, wait like some amount of milliseconds.
Yes, so there is no good reason to wait. So in the token, there are some differences between the token ring network protocol and token ring as we are going to use it for a lock. I'll come to that in just a second. As far as the network protocol goes, you basically held the token for a certain period of time and then you have to pass it on. Right? And we'll talk a little bit about, when I talk about failure properties, talk a little bit about what are the differences. Okay? But just so that people understand, this is derived directly from the use of token ring in network LAN systems. As you know, today nobody uses token ring for LANs. Ethernet has essentially taken over. Ethernet succeeded token ring, and there was no good technological reason why one became more popular than the other. It just looks like the companies that were marketing Ethernet were just more successful than the ones that were marketing token. As a protocol, it's fine. Now, coming back to our use of token ring for distributed locks, the big problem occurs when a token gets lost. Okay, so let's say the process that's holding the token right now crashes. Okay. Now what should you do? Yes.
So I think there is another big problem because if there are too many machines, and you must ensure all machines are in a circle, because if there is a shortcut and maybe some machine never get the token.
Okay. So point is, if there are lots of machines, they all have to be arranged in a ring, and that is going to basically limit the scalability of the system. You may have to wait a long time before the token circulate. There may be only a small number of processes that are interested in grabbing the lock, but the token still has to circulate through all the processes, and each process has to say, I don't want it, and I don't want it, and keep passing it until you get it. So there is going to be some latency involved. Okay? That is absolutely true. Yes.
Yeah, but it won't be a problem unless everyone's using the token and actually operating on it. Otherwise, it'll be circulating pretty quickly.
Yes. So I think that there are multiple ways to think about it. So even if n is large, you basically have to keep passing the token, but you don't hold on to it for a long time. So you will still have to, there will be some delay, okay, but that delay is going to be small. Okay. You cannot short circuit it. 3 cannot just send the token to 7. It has to circulate through the ring, okay, because that's the way the token ring protocol works. Because in the ring, essentially, you can only communicate with your neighbors. Okay, so I can only talk to I plus 1 and I minus 1. Okay, mod n. That's the way token rings work. Okay. Now coming back to the failure properties, detecting token loss is a non-trivial problem. Okay, if the process that holds the token goes down, then you have to detect it and recover from it. Okay? And there are some key differences between the way it was done in token ring used for LAN protocols versus the way you would have to do it here. Okay? And because the same kind of packets can get lost, right? The token is just a packet, the network can corrupt it and it will get lost, or the machine may actually crash, okay, while it's holding the token. Okay? So in LAN protocols, tokens, there was a way to regenerate the token. And the way it worked was as follows. Essentially, every node, even if it held the token, would hold it for a finite amount of time. Okay? This was ensured simply for fairness. Okay? Every node needs to get some fair shot at transmitting its packets on the network. Okay? So if node I gets the token, let's say it can keep it for 100 milliseconds, transmit whatever data it wants. If it has more data to transmit in 100 milliseconds, it has to let the token go and have the token come back. Simply does exactly the way CPU schedulers work and give time quantum. A process may need a lot of CPU cycle, but at any time it gets a quantum worth of time to execute on the CPU, and then it has to relinquish the CPU and wait for it to be scheduled again. Okay? That was done for fairness reason. Same thing was done for network protocol. Okay? Every time you got a token, you got a certain period of time T, for which maximum time for which you could hold the token. Okay? And then once that period has elapsed, then you are required to give the token to the next node. Okay? So what that meant is, in a token ring protocol, if there are n nodes in the ring, okay, and T is the maximum time for which you hold a token, every node should see the token once every n times T time period. Because there are n nodes, each can hold it for time T. So every n times T, you should see the token go by. Okay? So if you don't see it, you know that the token is actually lost. Right? So detecting loss of a token is much easier because you know that every so often the token has to come by. That's how the protocol has been designed. Yeah, then you can say that the token is lost and then run a protocol and regenerate the token. Okay? Now if you are using this for a lock rather than sending network packets, you can't actually enforce on the programmer saying you should write code such that if you get the lock, you have to give up the lock in time T. Okay, that's not how code works. You grab the lock, you do whatever you want to do in your code, and you relinquish the lock. There is no semantics saying you can only hold the lock for a certain period of time. Okay? So if you adapt that idea here, okay, you have to assume that any process that holds the token can hold it for an arbitrary period. You can't put an upper limit on how long the process can hold the lock. Okay? In that case, if you haven't received the token in a while, you cannot figure out whether the token is lost or some process is just in a very long critical section, just still computing. Okay? So it makes it much harder to detect the loss of a token in this case. Okay, so that's the downside of using this program. I mean, there is no simple solution to address that problem, simply because it's up to the programmer. If the programmer has long critical sections, it will take long periods of time for the token to circulate as each process gets the token. Okay, so there is no easy way to detect that a token has been lost. Okay, so that's something to keep in mind, that detecting failure and regenerating the token is not trivial. The network case, because of fairness, we had put a limit, okay, which we are not enforcing in this case. Okay. Any questions on this? There's a last slide here which I won't go into. We have looked at 4 different distributed locking algorithms, starting with a coordinator, and we looked at the Rickert and Agarwala. There was a distributed one that was based on voting, and there's a token ring algorithm. Okay, there are some properties which I will just summarizes the properties here. We'll just skip through that in the interest of time. Take a look, and if you see any problems, then ask. Yes.
So really both the distributed and the token ring algorithms, if any process crashes, they'll all go down, right?
Yes.
Because the token will eventually get to the crash node and be done.
Right. So in both of the distributed cases, if any process that holds the token crashes, there's a deadlock. Because you cannot, as I said, you cannot distinguish between a slow process and a crash process in a distributed system. A crash process is simply an infinitely slow process. Okay? So unless you enforce some other semantics saying I can force a process to relinquish a lock, which you don't do in a real system. Unless you put some other semantics like that, it's going to be very difficult to recover from a failure. In the centralized case, you have a different problem. The coordinator has crashed, not the process that's necessarily holding the lock. Okay? Even in that case, if the process holding the lock crashes, you are deadlocked. So that problem still exists. But you have one more problem, which is if the coordinator of the lock crashes and all the other processes are alive, and still there is going to be a problem. Okay? So if you have coordinator crash, you have to detect that the coordinator crash, recover from it, and figure out what the state of the lock is when the coordinator crashed. Because only the coordinator knows whether it was in use or whether it was actually free at that. So the point being, implementing distributed locks correctly is not a trivial problem, okay? Especially in scenarios of failure. If you assume a case where there are no failures, or you only want the lock to work in when there is no failure, then all of these techniques work well. Okay? And then if there's a failure, then maybe all you have to do is just terminate your application and reboot or something. If you are willing to do that for the application, then you don't have to deal with the failure case. Otherwise, this becomes a problem. So that's distributed locks, and that sort of leads nicely into the next topic, which is on distributed transactions and how you use locks to implement distributed locks. That is, to implement this notion of transaction. Okay, so transactions are concepts that is a concept that is used widely in databases, as you probably know. So I'm going to quickly review what we need to know as far as transactions are concerned. And then we'll look at distributed transaction, which is what is of interest here. Okay? So as you probably know, what transactions do is they are a higher level primitive that allow you to implement atomicity for a critical section. Okay? If you have a piece of code and you wrap that around a transaction, that allows you to get properties of critical section, which essentially mean when that transaction is executing and is modifying certain, let's say, data in the database or any data structure, no other transaction will be allowed to do the same thing at the same time. And moreover, you will basically get this property of atomicity, which is all or nothing. Either the transaction finishes completely, okay, or it basically doesn't finish, which means all the changes that it did are undone. Okay, so you get this notion of atomicity for this critical section, which locks by themselves will not give you. Okay, so there is no notion of rolling back state when you have a lock, but transactions allow you to roll back, as we will see. Okay, so they have their origins in databases. Okay, and now we are going to look at an example of why you need to implement transactions. In particular, a very simple example, two clients that are trying to write to a database. Let's say there are two clients that are trying to update a banking database where there are records of what each account balance has, and then you are modifying that. Okay, so the basic operation that we are trying to do is as follows. Client 1 is trying to transfer $4 from account A to account B, and client 2 is trying to transfer $3 from C to B. Okay? Essentially, if both of those operations succeed, the account balance in B should have increased by 7. Okay? Because one is transferring 4, the other one is transferring 3. Okay? And we'll assume that both of these requests are executing in parallel. Okay? So if you did not have this notion of a transaction, or in this case all you need are locks actually, not even transactions, then you will get inconsistencies as is shown here. Okay? So these are the operation client 1 does, this is the operation client 2 does. Okay? So client 1 is going to read the account balance for A, and then it's going to deduct $4 from that account. Okay, then it's going to read the account balance for B and add $4. That's transferring 4 from A to B. Okay? Client 2 is doing the same thing. It's going to read C, subtract 3, read B, and add 3. Okay? And we'll assume that these two operations are occurring in parallel. So this table actually shows a time sequence in which these operations can actually execute and result in an inconsistency, because we have not used locks or transactions at the moment. Okay, so these are the time steps. Step 1 is balance is read, then you subtract 4, and then client 2 starts running, okay, for whatever reason, then you read C, and then it subtracts from C. Then you read B, okay, which is $200, and then we switch to 2, you read B, again that's still 200, you add $3 here, and then you switch back to A, which has already read the old balance, not the new one, and you're basically going to overwrite the account balance that was updated. So this value gets overwritten by this value because they are both of those are actually executing in fact. So this clearly is inconsistent because what we would have wanted is if both of these operations succeeded, the account balance of B should have increased by 7, not by 4 or 3. Okay, so this is a very simple example to show A, you should have used locks, which shouldn't have happened at all, first of all. Okay, and B, you actually need more than locks, you need transactions, as we'll see, to give us even stronger properties. Okay, example clear, right? Right. So most transactions in databases provide what are called ACID properties. Okay, ACID is an acronym for atomicity, consistency, isolation, and durability. Okay. Atomicity essentially says you should be all or nothing. Either the whole transaction should have executed as one logical unit without seeing any other impact from other transactions, or it should not have executed. So what we would have wanted is something like this. Okay, either this one runs and then that one runs, or the other way around. Okay, interleaving them yields, gives us inconsistencies. Okay, so although they are actually executing in parallel, the result should have been as if they happened in that order. Okay. So we want atomicity, which is all or nothing. Consistency basically says that if the system is in one consistent state, after a transaction has executed successfully, it should again be in the consistent state. Okay, so this interleaving was not consistent. You went from a consistent state to an inconsistent state. Okay, so that should not happen. Okay. Isolation is also referred to as serializability, which basically says that you want to ensure that even though there is an interleaving, there should look like they actually executed one at a time. Okay? And you want durability, which says that once you write some changes to disk, then they are permanent. You can't undo them. Okay? Until then, you have the option of undoing something. Okay? Now, you could say a very simple way to implement some of these properties is just use global lock. Right? You take the entire database, you put a lock on the data. So when client 1 runs, everything is locked. Okay, so you read A, write A, read B, write B. Client 2 might try to run at the same time, but it cannot proceed at all. Okay, because you grabbed a lock on the whole data. It's going to block until 1 is finished and then 2 will start. Okay? It's a simple solution to addressing all of these problems. Okay? But as you can imagine, in a database system, if only one transaction can actually execute at any given time, you really are going to get sequential execution. There will be no parallelism or concurrency. Every other request that is coming in will have to wait and block. Okay? And many transactions may be operating on independent records of the database. Okay? So somebody is trying to withdraw money from their account. If I am withdrawing money from my account, should I block that person because my ATM has locked the entire database? Doesn't make sense. Right? So you want parallelism as much as possible. You don't want to implement global locks and reduce concurrency. Okay? So the question is that locks will give you the property we want, but they're far too restrictive. Okay? So most databases will not actually do what we just said. They will be smarter. They may actually have record level locking, which means you can lock not the whole database but a particular record of the database and not other records. Or they will actually do something smarter like optimistic concurrency control and so on, which we will all look at. So we want to get these properties which locks give us, but we want to be smarter. We want to ensure there is more parallelism. We want client 1 and 2 to run at the same time. Okay? And yet we want consistency. We don't want the problem that we saw on the previous slide. Okay? But we have one additional option here, which is because we are implementing these operations as a transaction, we have the option to undo, which means we can let client 1 run, but before it finishes, you can check, did something happen that may result in an inconsistency, and you have the option of saying undo everything that 1 has done and go back to where 1 started or 2 started. And typically when you write code, you don't have the option of undoing something. Okay? Here we have the option of undoing, so this is called a rollback of a transaction. Okay? Because we allow more fine-grained concurrency, we will also allow the option to undo changes. Okay, so yeah, now with that very sort of brief background as to what databases and transactions do, let's look at distributed transactions and see how some of these ideas work. Okay, so we'll assume that there are simple primitives here, begin transaction and end transaction, allows you to take any piece of code and wrap it with these two statements, begin and end. And then the assumption is whatever code is executing in between is going to basically get all the asset properties. Okay, so it's all or nothing. You'll get atomicity, consistency, isolation, durability, all of those properties would be true. Okay. So here is an example where you're making an airline reservation. Okay. And basically, let's assume you want to go from, in this case, New York to Delhi. Okay. There's no direct flight. So you're going to basically book a sequence of legs. Okay. And the entire reservation will succeed only if you manage to get a seat on each of those individual legs. Okay. You don't want to get 2 legs and not booking on the third, then you cannot actually travel to your destination. Okay, so it's either all of them or nothing. If you cannot find a seat on at least one of these 3 legs, then you should say that I cannot book on that route, try something else. Okay, so this is why transactions will help you. Okay. Now a seat on each of those flights is itself another transaction, which we'll ignore for the moment. But basically the transaction says reserve a seat on this flight, and this flight, and this flight, and if all of them succeed, then it has, the whole transaction has succeeded. If any one of them fails, then undo whatever you have done. Yeah, because let's say the first 2 succeeded, but the third did not, then you have to clean it up. You can't leave those 2 seats hanging there because now the booking as a whole has failed. Yeah, so that was what abort transaction will do. It will roll back the transaction. It will undo whatever the reserve method here did for you. Okay, so you basically abort. Okay, that clear? That's an example of a transaction. And now I'll talk a little bit about what nested transactions do and what distributed transactions do. Okay? The nested transaction is similar to an example on the previous slide. Okay? The transaction itself has smaller transactions in there. Okay? So for instance, to make a travel booking, you may want to do both an airline booking and a hotel booking. Okay? Each of those are individual transactions because they may actually even operate on different databases, an airline database and a hotel database. And you want the entire booking to succeed only if you can get a plane ticket to go to your destination and a hotel room. And if either of those 2 don't happen, then you want to abort the whole transaction. The way you will do this is you will do the airline booking as one transaction, the hotel booking is another transaction, and you will wrap both of those transactions in another bigger transaction. Okay, so if either of them fails, you can undo both of them, or either of them. Okay. This is referred to as a nested transaction, where one transaction is nested inside another. Okay. And this is done in traditional databases already. Okay. What we want when we talk about distributed databases is slightly different. This is also an example of distributing a transaction, but we are actually going to focus on the second picture there, where your database itself, okay, is distributed on different machines. Okay, it may be partitioned or replicated on different machines. And this entire database gives a logical view of a bigger unified database to all applications that are accessing it. Okay. And now when you try to do a transaction on this, you will actually have sub-transactions. Okay, maybe you are booking a ticket from the United States to Asia. Okay, maybe the Asian segments of this airline is actually stored on a separate database that's hosted in Asia for whatever reason, and so once in North America are hosted here. So the airline database itself may be split, okay, because no single database may be large enough to store all of the records. Okay. So to perform this transaction, you have to actually go to smaller copies of the database or replicas or partitions and perform operations on it. Okay. So your transactions get split into smaller sub-transactions, and you have to still provide those asset properties. And that's what we are going to focus. Your sort of a single centralized database has become distributed, and we still want transactional properties. Okay, is that clear what we are trying to do? Okay, so we'll talk about 2 techniques to implement transactions, and then I'll come back to this notion of a distributed database and locking and so on. Okay, so given any transactional system, okay, there are essentially 2 ways you can actually implement this notion of a transaction. So the basic idea is you need the ability to roll back your changes. If the transaction fails, then you need to be able to undo things. Okay, so the question is, how will you do that? Okay? So at a very simply, there are 2 high-level ideas on how you can do undo. Okay? So the way you can do undo is the following. Rather than, so if you have a copy of some, let's say a file, let's forget databases for a moment. Let's say you want to write to a file, but you want the ability to undo your writes. Okay, if that write is inside a transaction. How would you do it? Okay. First idea is, rather than actually writing to the file, make a copy of the file. Okay. Write to that copy and then check, is the transaction going to succeed or not? And if you succeed, then copy your changes over. Okay. And if not, just throw away the copy and then you are automatically undone because you never touched the original data to begin with. Okay. So one way to undo is make a copy, operate on your private copy, and then only propagate the changes if the transaction succeeds. Otherwise, just throw the changes away and you're done. Okay. That approach is called private workspaces, where the copy is called a workspace. You basically, so here is basically sort of blocks of your file or your database. In order to have a transaction that operates on it, you just make your own copy and you operate on that copy, and then if the transaction succeeds, you commit all the changes. Okay. This is one approach. The other approach is basically you don't make a copy, you actually operate on the original data itself, but then you have to keep track of what changes you made so that you can undo them. Okay. The way this is done is you keep an extra set of information called a log. Okay, the log tracks every write you have made. Okay, it also tracks the before and after state of whatever you did. Okay, so what you have is something called a write ahead log. So let's say you have a file. Okay, and let's say write is going to basically go modify the ith block of the file. Okay. What you will actually do in the log is you will keep a copy of the old block and you will keep a copy of the new block and say that at time t there was a write to block I, this was the old value and this is the new value. Okay, in the database you will do the same thing. You will actually keep a copy of that record so that you can figure out what was the old value. The only way to undo is you have to keep track of the state before, okay, the state of the record before, and you have to, so that you can replace it. Okay. So you will keep this log, and if the transaction commits, there is nothing to do. The transaction doesn't commit, it aborts. Then you go back to the log saying I have to undo all these writes. Okay. So tell me what writes actually took place, that's number one. And tell me what modifications they made so that I can go back to the old version and then put that back into the data, whether it's a database or a file. Okay. This is referred to as write ahead log. Okay. So essentially you can then use the log to do a rollback. Okay. You can go back and just undo all of the changes. Okay. Those are not the only reason to have logs, transactional logs in databases. You can also use them to recover from failures and so on, which I will not talk about at the moment. Okay, here we are only going to talk about transactions that are aborting and are going to come back. Okay. Now the last point is you have to make the transaction atomic. Private workspaces and write ahead log give us the ability to undo, but they haven't told us how to make things atomic. We haven't used the notion of a lock yet. Okay, we need to do that. We'll come back to this in chapter 7 when we talk about two-phase commit and so on. Okay, at the moment, we are going to ignore that problem. Okay, here let me give you an example of write ahead log. Okay, so we'll assume that there's a transaction, it operates on just two integers. Okay, it's very simple integers that are stored on disk. And this is the transaction, it has three operations. It basically adds 1 to x, adds 2 to y, and then does square of y. So as each operation takes place, this is what the contents of the log is. Okay, so log says basically original value of x was 0, the operation has actually changed the value to 1. Okay. Then in the next step, you basically say original value of y before this operation was 0, after this operation it became 2. Okay, then you say whatever you did there, which is x is y square, so you say y value of x was 1, and now it became 4. Now if the transaction aborts at this, so at the end of this, y is going to be 2 and x is going to be equal to 4. Okay. And if you decide that you want to throw away the transaction aborted, you'll simply go back to the log backwards and just replay. Okay. So what you will do is you will say, okay, value of x is 4, change it back to 1. Okay. You will say value of y is 2, change it back to 0. You will say value of y is 1, change it back to 0. Okay. So now after you've done this, x and y will be reset to 0. Because you're just going backwards and replaying whatever the values were. Okay. So this is just log replay backwards to undo the impact of a transaction. Yes.
So would you actually need to keep every modification? Why not just keep the initial state before the transaction and then you can replay directly back?
Okay, so that's a good point. So point is, would you need to keep every record of whatever has happened? Why not keep a copy of the thing before the transaction and then after? Okay? If you knew what the transaction was going to modify, you could have actually done that. You could have said, think of a large database, 1 gigabyte in size. This transaction modifies 2 records. Okay, but when the transaction begins, you don't know what it is going to do. So one thing is you get a copy of the entire database before, and then if you want to replace it, you replace. But then you copied a whole lot of data for no good reason. Okay? So it is probably more efficient to only keep track of state that is being modified, because the total state is assumed to be much larger. Maybe there are 100 other variables that we did not even touch in this transaction. That's the reason you do this now. But as you do this, you will see that there is some wasted information. X is modified twice, you have 2 records here. All you had to actually do was replay that, not necessarily this, but we'll ignore all those optimizations. Okay. The only issue is you could have actually kept state of the whole system before and after, and then you don't need to track anything. So you just revert back to old. But taking that snapshot is going to be more expensive. This is better to do. Okay. But what you said is actually we'll come back when we come back to failure recovery, fault tolerance. You'll see that that approach is actually used. Periodically you checkpoint and take a snapshot of the entire state, but between checkpoints you keep a log. Okay, so rather than rolling back to the checkpoint, you can roll back to precisely the instruction where the crash occurred. Okay. So you are willing to, because the log can grow over time. Okay, maybe there are lots of transactions, there may be millions of records in the log. So replaying that may be just as expensive as taking a snapshot. So once in a while, you want to take a snapshot and then only keep logs from that point on. So you can combine these ideas. We'll come back to that when we do fault tolerance. Yes.
In a distributed database, I mean either partitioned or replicated, is the log in a central place, or is it distributed on every machine that you have the copy of the database on? Because if it was distributed, then when you're trying to replay it, you have to first collect all the logs from every single machine and then try to replay.
Okay. So question is, if your database is distributed, where is the log stored? Is it going to be stored in a central place, or it's going to be stored on each of the machines? Okay. When I explained this concept, we actually have completely ignored whether this thing is distributed, centralized, or X and Y on one machine, separate machines. We sort of just glossed over all of those issues. But if you actually implement distributed transactional system, you have to worry about that. Okay. There are many approaches on where you keep the log. The simplest approach, going back to the distributed transaction case, the simplest case is each sub-transaction will log whatever it is doing locally. Okay? If the entire transaction as a whole commits, there is nothing to do. The transaction rolls back, then you have to roll back the individual records of each of the logs here. And since you actually keep track of the transactional ID for each of the logged values, okay? You know what to roll back. Bringing all of the log information to a central location may be problematic, and in any case there may not be a central location. The whole point is a fully distributed system. There is no central coordinator in some case, so there is no single place to put it at all.
So again, you need some concept like a Lamport clock or something to implement the logging facility, because you need to know what to roll back when. For example, one this thing might have happened here, another operation might have happened on another database. And
right. So point is that if you are actually going to log them in a distributed scenario, do you need timestamps? Should you assume synchronization? Are you going to use Lamport's clocks? So keep in mind that each transaction is operating independently of other transactions. Okay, so the way transactional systems work is they are not going to actually use Lamport's clocks to say this transaction goes first and that. So the idea is all transactions are actually going to get some notion of a lock, and they are going to operate independently of one another. So when you are rolling back something, you are only rolling back for a given transaction, not for anything that other transactions have done. So all we need to track is what changes transaction I has made. Okay? And we don't worry about entries in the log that have anything to do with other transactions. There may be 100 other transactions and there will be log entries there. And when you are rolling back a transaction, we just ignore them. We only focus on what this transaction has done, which in this case are precisely these entries in the log, which will be tagged by the transaction ID. So each transaction will get a unique ID. So you'll say transaction 10 did this, did this, did this. And there may be other entries in between which we are ignoring. and will be tagged with other transaction ID. So if this transaction aborts, you're only going to look at these entries. Okay? So it doesn't matter what has happened with respect to other transactions, when they happen, none of that is important for rolling back this transaction.
Even in this transaction, you need to know what operation happened first. Like you need to know the sequence of operations that operated on the data.
Yeah. So point is, do you need to know the sequence of operation that happened on the data? And I would basically say, if the transaction has become sort of several sub-transactions, each of them are operating here, you only need the sequence on each of those. You want to roll it back completely. Okay? So if you basically modified value X here and Y here, you're going to roll back those values and you'll go back to where you were. Okay? And I think so. What you are asking is, if these operations are happening on different machines, okay, do you need to know the ordering? Okay? In general, yes, but if you're not replicating the data, you don't need to worry about it. They're independent values. If you undo each of them, they'll go back to where they were. Okay, you had a question.
Yeah, it was somewhat related. I was just curious whether transactions could happen concurrently and would be working on the same resources at the same time.
Yes, so question is, can transactions actually execute concurrently and operate on the same resource? We precisely want that property. This is called concurrency
So
control.
in that case, we when rolling back one transaction, would there be a case where we'd have to roll back a completely independent transaction? But,
so that's a good question.
Because it could possibly be changing a value of X on one particular transaction midway through another one.
Yes. So good question is, your concurrency within transaction, across transactions rather, they're all operating on, let's say, similar values. Can rolling back one transaction impact another transaction? This depends on what the concurrency control algorithm does. Okay, so we'll look at scenarios where there are things called cascading rollback. You abort one transaction, it undid something. Because it undid something, another transaction that may have taken the output of this transaction cannot proceed anymore, because it's already taken, let's say, the value of Y and done something. Now if this Y is being reset from 2 to 0, any transaction that did 2 and did some computation will also have to roll back. Okay, so you may get scenarios where there will be cascading rollback. But there are other cases where you will not see that. If you have private workspaces, you will not see the value of these transactions being output before the transaction commits at all. Okay, so the answer is, it depends on what concurrency control does. Okay, you may get scenarios where aborts actually get cascade, and you may get scenarios where they're totally independent. You don't have to worry. The private workspace scenario, since you're operating on your local copy, any changes transaction I has made is not even visible while the transaction is executing to others. So if this transaction aborts, others did not even know of its existence to begin with. It has no impact. Okay, but if you are doing write-ahead logs, this kind of problem might actually occur if you do things like optimistic concurrency control. We'll look at that next. Okay. Any other questions on this? Okay. So that actually brings us to exactly this restriction, saying if two transactions that are executing concurrently cannot access the same record. Maybe 10 people are all can try to book a ticket on a plane. You can't say person I is trying to book a ticket, so I'm going to let everybody else wait. You should let anyone come in and do whatever they want and still have all of the properties that we wanted. Okay, so each transaction may be executing concurrently, but the collection of manipulated data should still leave the system in a concurrency. Okay? So you want concurrency, but you want the output to look like each of them went sequentially. Right? Because if you go sequentially, we know that things are right. Okay? But you don't want to prevent, say, or you don't want to enforce that things only happen sequentially. You want to have concurrency, but you want to get this property called serializability, which is the output should have been as if they actually went one after another in some order. If that is the case, then we are good. Otherwise, you have inconsistency. Okay, so achieve consistency by ensuring that they occur in some certain order. We'll see how to implement concurrency control. Okay, so you can do that in a layered fashion. This is typically how things work in any database. So you will have what is at a higher level what's called a transactional manager. Okay? This is the thing that is tracking when a transaction begins, when it ends, keep all the logs for the transaction and so on. There is, once a transaction begins, before you read or write any data item, you may actually have to get fine-grained locks. Okay? Now you don't log the whole database, but many databases will allow you to lock a record. They may even allow you to lock a field of a record. You can just lock the employee ID or whatever the field says. Okay, so if the database supports fine-grained locking, then the scheduler is actually going to do the locks for everything that this transaction is accessing. The scheduler will internally go get a fine-grained lock for that operation and then release the lock once it's done. Right? And then you are the data manager. This just simply once the lock has been acquired, you are going to actually do reads or writes. Okay, so the layered approach. And then at the end of each transaction, the transactional manager says, is everything consistent? Okay. So did something happen that requires us to roll the whole transaction back? If so, you are going to go undo everything using the write ahead lock. If not, then all the changes that are actually being made are committed. Okay. They are made durable. At this point, transaction cannot be undone. Okay. So transaction manager looks at the whole transaction and says, is everything consistent or not? The scheduler is looking at individual operations within the transaction and trying to grab locks. So for instance, in this case, before accessing X, you just grab a lock on X. Once you're done with the operation, you release it. Before operating on Y, grab a lock on Y, release it. So the scheduler will do the smaller operations. The transactional manager will look at the whole transaction and say, should it be allowed to commit or abort and so on, and keep track of the write ahead logs and things like this. That's how typically transactional systems are implemented. And if you have a distributed database, you will basically get a set of machines, each of them hold a portion of the database. You assume that the transactional manager is still logically unified, but there are schedulers and data managers on each machine to allow locking of individual records on those machines and reads and writes to those records. The transaction as a whole is operating on the whole database. So there's one transactional manager, okay, logically. So this is basically the picture to keep in mind. Okay. Okay. So I'll introduce this notion of serializability, and then we will actually look at some concurrency control technique. Okay. So the assumption we have made is we want concurrency. Okay. We want transactions that are even maybe operating on the same set of records to all operate in parallel. Okay. And what we want is, at the end, you want to have what we mean by consistency is if you are left in a state that you would have gotten if they had operated in some sequence. Okay. And then whatever that sequence may be, then we are in consistent state. If you don't see that, then you are in an inconsistent state. Okay. Here's an example to show what serializability would actually mean. Okay. So these are three transactions. They all operate on this sort of very pathological case, but they all operate on one record, which is X, okay, one integer in this case. Okay, and each of them it does something different to X. So each transaction is actually resetting the value and setting it to some other value. Okay, so this transaction actually sets the value of X to 1, that one sets it to 2, and that one sets it to 3. Okay. So now you can ask the question, regardless of which order this transaction executed, what are valid values of X at the end of this operation? Okay, what values are we willing to accept? That would be serializable. 1, 2, 3. Okay, so it should be 1, 2, or 3 because basically you have to take all possible orderings of these transactions. You could say one possible ordering is 1, 2, they are executed in order 1, 2, 3 if they were operating sequentially. Okay? And then we'll take whatever actually is the output of executing as 1, 2, 3 or 1, 3, 2 or 3, 2, 1. Pick any ordering. Okay? Any of those orderings we'll accept as valid, even though they're actually executing in parallel. And given these orderings, you will see that the only valid values that we'll accept are X equals 1, which is basically this one executed last, or X equals 2, this one executed last, or X equals 3. Any other value or any other interleaving we are going to reject as inconsistent. Okay? So because now they are actually executing in parallel, you will get an interleaving of those 6 instructions, and you may have, they actually might execute in this order, or this order. Okay. So you'll see that what you have to see is what's the output of each of this. So if they execute in this order, essentially that transaction went last. Okay. So you'll end up with X equals 3. You'll say that's legal. because that is a possible serializable order. Okay. In this case also you will end up with x equals 3, we'll say that's also fine. In this schedule you will actually end up with x equals 5, okay, because you said x equal to 0, then the last instruction there executes, which takes it to 2, and then this one executes, that takes x equals to 5. So this interleaving will give us a value of x is 5 at the end of that interleaving. And we said that is invalid because there is no possible way to execute these transactions in sequence and ever get x equals 5. So yes.
So what if the operator say if the approach, so schedule 2, so we need to change the schedule.
What's the question?
So if the transaction say is the approach,
Yes.
and it will send the x back to 0, right?
Yes.
So actually is wrong because if after the AB execute, x should be 3.
So you are asking what happens if the transaction actually aborts,
Yeah.
right? And what should be the value? So if you abort, you will undo whatever that transaction did, maybe not others. But at the moment, we are not even asking about what to do if you abort. We are just asking what are valid ways to execute these instructions and still be left with a consistent state. Okay, and all I was pointing out, so we'll talk about aborts in just a moment. All I was pointing out is x equals 5 is not a valid state. If your database says x equals 5 after you implement these 3 transactions, you will say that's inconsistent. There's no conceivable way by which I execute them one at a time. Okay, pick any order where you execute them one at a time, okay, and you will never get x equals 5. Okay, so that's inconsistent. But the other two are legal. Okay, so that's what serializability means. This is a very simple example to demonstrate what it means and what orderings or interleavings are invalid. Okay, how to get a valid interleaving we haven't said. Okay, this is a trivial example to tell us what it means to begin with. Okay, now to come back to your point, if you actually get something like this, you would have to abort the transaction. Okay, you would basically have to roll them back. In this case, you may even get cascading aborts.
Even in this case, if we cancel, say, transaction 3, we're left at an illegal state in schedule 2.
Okay, in this case, if you undid transaction 3,
Yeah.
what it would do is it will basically
Undo the last 2 steps in schedule 2.
yes.
So we're left with x equal to, 3.
You will actually be left with,
You'd have the same result only, but as an unintended consequence of the other 2 transactions.
in this case, you have, what we will have is what is called a right-right conflict. Okay, with this interlay, you might have to undo multiple transactions, not just one. Okay. Even though just undoing one might give us an interleaving, but you don't know that. The transactional manager just sees 2 transactions, try to write to this. The safe thing to do is undo both of them. Okay. Even though if you actually look at the code and you say, if I only undid one, that's still valid, but the transactional manager doesn't know what's in the code. It's only seeing what are the values, how they're changing, which transaction wrote to what record. Okay, so it might actually end up undoing multiple of those. Okay. So then question really is, what kind of locking scheme should we actually use to get concurrency and yet serializability? Okay. There are many different approaches here. Okay. We'll start with the simplest one. The simplest one says, let's not do anything. Okay. Let's be optimistic that most of the time transactions are going to operate on different parts of the database and they do not conflict at all. Okay. And if that is the case, then let them just run with, let's not even implement any lock. Okay. Let them run. And at the end of each transaction, we will see were there any 2 transactions that basically operated on the same set of records. If the answer is no, which is probably true most of the time, then we will not do anything. If the answer is yes, then we will terminate all such transactions and then redo them, rerun them. Okay. This is referred to as optimistic concurrency control, the do nothing approach. It's a lazy, called a lazy approach. Lazy approach says, let's not implement the overhead of locks. Most of the time you pay all this overhead, but transactions are doing different things on different parts of the database. They are not even conflicting. You have all these overheads. Let's ignore all of that and just pretend like we don't need locks, and most of the time we will be okay. Okay? Now, so basically you will use, this works very well with private workspaces. because every transaction gets its own copy of the database. Okay. It does whatever it wants to do with that copy of the database. Before you commit the transaction, you check, did any other transaction in the meantime modify anything that this transaction is modified? If yes, abort. And if no, you're fine. All these transactions that came into the airline database, people are looking at seats on different flights, they don't conflict, so let it be, nothing to do. Okay. So the advantage is this is by definition deadlock free. Okay, that should be clear. Why is it deadlock free?
You don't have any locks,
No locks, so I can't do deadlock free. No lock. Okay, maximum parallelism. Okay. No locks means no blocking. Okay. Transaction comes, it just starts executing immediately. Okay. So good advantages, but there are some disadvantages, which is that there may be, whenever there are conflicts, you will have to abort the transaction. Because if there are conflicts, you cannot even tell whether both the transactions actually did something in a serializable order or not. You can only play safe and say, these two transactions touch this data item, common data item. That can be a problem. I don't know if it's a problem, but I'm going to have to just rerun it, because there's just no way to track what happened. Okay? So rerun the transaction if it aborts, and the big problem really is as the load on the system rises, okay, the probability of having a conflict and abort keeps going up. And because as more transactions come in concurrently, the probability that any two actually touch the same record keeps going up. Okay, so at high loads, you may actually do a lot of wasted work, because you will see some conflicts, you will abort them, you have to rerun the transaction clearly. Right? So you will rerun. So your system may be heavily loaded, but a lot of the transactions are just aborting and being rerun, and they will keep aborting and rerunning over and over again. Okay? So at high load, you will basically do a lot of wasted work. Okay? So that's a disadvantage of the approach. Okay? So
isn't then in that case isn't the advantage of maximum parallelism kind of artificial?
Question is the
Because
advantage of maximum parallelism artificial? Yes, you get the advantage of maximum parallelism only up to a point. Above some threshold where the probability of conflict rises above a value, your good put will drop. You will do a lot of work, there will be a lot of computation, but no transaction is actually making progress. They keep getting terminated. So you get that advantage only up to a point, and after that you are basically in a bad situation where good put is. Throughput is high, but good put is not. Good put is number of successful transactions. Throughput is how many transactions are running. And that keeps going up, but good put keeps dropping. Okay. Now, so there has been a lot of work done on optimistic concurrency control, how to implement it and so on. Okay, but as it turns out, no commercial system actually implements it today. Okay, pretty much so the other flip side of concurrency control is what is called pessimistic concurrency control, where you actually use locks. Right? Optimistic doesn't use lock at all. Okay, so every system that you see, commercial system that you see, actually uses pessimistic, where they actually use locks, they don't use optimistic. Okay? Even though it has some of these properties and lots of papers have been written. Okay? And I think the simple reason is you cannot sell a product where you tell the customer after 80% utilization you are not going to see any progress. The system will stop doing anymore. So people don't like that, right? So I think for that reason, because of that uncertainty of what might actually happen, most databases take a conservative view. Say let it work. Maybe more transactions will be blocked if there are locks and lots of transactions come in, but that's better than having them run and keep aborting and doing wasted work. So that's the view that commercial systems take. Okay. On the research side, you will still see a lot of optimistic concurrency control style algorithms. Now, if you assume you want to do pessimistic concurrency control, you will actually have to implement some form of locking. There are many approaches to doing it. The one that I'll just briefly describe is this notion of a two-phase lock or 2PL. Okay, so there are again a distributed version of this and a centralized version of this. But the basic idea is very simple. It's sort of shown in this picture. Okay. So it shows how you should acquire and release lock within a transaction. Okay. So every transaction that implements, or a transaction system that implements pessimistic concurrency control and two-phase locking basically does the following. At the beginning of the transaction, you will start getting locks as you touch more and more records. Okay? And so that's called the growing phase of the transaction. You keep acquiring locks. Okay? After a while, basically you start releasing locks, and that's the shrinking phase. Okay? And the rule is as follows. Once you start releasing locks, you cannot acquire any more locks. Okay? So either you acquire locks and keep acquiring them until you are done. You don't need to touch any new data items in your transaction. And once you are done, you just release them all. So this idea is called two-phase locking. There are two phases to your locking protocol. A growing phase where you say acquire, 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 then do whatever computation, and once you start releasing one, you cannot acquire anymore. You can only keep releasing. And there are some properties that you may ask, why bother doing all this? What does this give us? Right? So there are some properties here which says that if you do things in this order, okay, you may actually try to avoid. And there are some more restrictions. If you put them, you can actually avoid deadlock. The whole point we are trying to have is pessimistic concurrency control needs to acquire locks, but you want to avoid deadlocks. Okay, so what should you do to avoid deadlocks? You have to enforce some restrictions on how you acquire and release locks. If you don't enforce those restrictions, you are going to get an immediate deadlock. Okay? So I presume you know the standard example of a deadlock where, let's say, you have a begin transaction. Okay, you will basically say, you do something to X, and then you do something to Y, you end, and then there's another transaction which basically does things in the other order. Okay? Now if you let this transaction run and you say this transaction run grabs a lock on X, okay, then you switch here and this transaction runs and grabs a lock on Y, and then the first transaction tries to acquire a lock on X, Y, which this transaction holds. This transaction tries to do the same thing, and you have a deadlock. Okay? So if you just simply implement concurrency control and let the system acquire locks for transaction in arbitrary order, you are going to get deadlock. You want to avoid that scenario. Okay? There are multiple ways to avoid the scenario. First is you want to ensure that you will actually have a growing and shrinking phase that will prevent problems. Okay? The second thing you also want to do is enforce a ordering on in what order do you actually acquire locks. Okay? The only way to actually prevent this scenario is to order these resources somehow. Saying this transaction needs a lock on X and Y, and so does this. And then if you say that regardless of the order of operation, you have to first grab a lock on X and then grab a lock on Y, then this transactions will proceed smoothly without a deadlock. Okay, so you have to analyze what locks you need, you order them, and you always acquire them in that increasing order. If you acquire them in that increasing order, you will not have deadlocks. If you reorder these things, then you will actually get into these problems. Okay, so the reason I'm mentioning this, although we have really little interest in database systems, the reason I'm mentioning this is you have to still do locks in distributed applications. And if you implement them using these sound ideas, you will not get into trouble with deadlocks and so on. This question.
Isn't one of the whole points of transactions that we don't know what locks we're going to need? Like otherwise we could just say, all right, lock it and then do my operation.
Yes. So the point of, so that's a good point. The point is the transactional system may not actually know what locks do you need, right? So you may not actually do it. So as it turns out, the way transactions work is you send off a query to a database. Query is some code. Okay, you could, in theory, actually analyze all of that code, okay, if you wanted to, and say this is what a transaction does. These are all the instructions it's going to execute. This will require you to actually acquire this locks. If you do that analysis, you can assume that you know. Okay? If you don't have access to that or you don't do that analysis, you just execute instructions on that query as they fire, then you will not know. So it all depends on what assumptions you make. The safe thing to assume is you don't know. Okay, but typically the way it works is you have to actually ship the entire query to a database before it starts executing. So there is a lot of analysis that happens in terms of query planning and all of that. So you analyze the query to do a lot more things than just locking, to actually figure out how you do joins and all of those things. So it is a reasonable assumption to assume you can analyze it and figure out an order if you wanted to. Okay, if not, then you have to actually make even more pessimistic assumptions and do something on the fly. Okay. So the basic point is, when you do a pessimistic concurrency control, you will have to acquire a sequence of locks, and if you enforce a restriction on the order in which you acquire them, okay, regardless of the order in which the statements execute, you will get you will not get any deadlock. Otherwise, you will basically get a deadlock if you acquire them in different order like I showed you. So concurrency control systems have to look at all of these issues. I'm not going to go into a lot of details of specific concurrency control systems out there, other than to say that two-phase locking is basically one way to do it, where you go and do all of the acquisition and then you do a release, and that gives you some property which says under certain scenarios, if you have this ordering and you do that, you will never have deadlocks. Okay. There's something called strict two-phase locks, which basically says you still have a growing phase, but then you release all the locks. There's no shrinking phase. The shrinking phase is all at the end. All the lock release actually happens when the transaction ends. Okay, so this is referred to as a strict version of two-phase lock. Okay, this is basically a stricter version than this, where you don't keep releasing, you just release at the end. Okay. From a concurrency perspective, normal two-phase locks will have more concurrency, okay, because you are releasing locks as soon as you are done touching that record, so some other transaction that was blocked can proceed immediately. But then if you have to release them in a right order, otherwise you will have some problem. And this is more conservative. It just acquires locks, waits for the transaction and releases them in one shot. You get less concurrency, but it's easier to implement. Okay, you don't have to worry about what order to release them and so on. Okay, you just release them all at once. Okay. The last approach I'm going to talk about very quickly, we have run out of time here, is timestamp based concurrency control. So in this case, we are going to go back to our idea of Lamport's clocks and use timestamps on Lamport clock timestamps in particular to reason about whether there was a conflict and what to do about the conflict. Okay, so I'll mention quickly the basic idea. I'll come and discuss that next time. So every transaction that starts off is given a timestamp. This is a logical clock value. Okay. So basically then what we have to do is use that timestamp to detect whether this transaction actually has conflict, any sort of a conflict with another transaction. And if the answer is yes, then you are going to abort that transaction. And we will use timestamps to reason about is there a conflict or not. So in particular, we are going to use the timestamp of the transaction to also timestamp every record that is modifying. And we'll use the record that has been modified and reason about the timestamp of the transaction, the timestamp of the record, and say, is there a right conflict or not? Okay? And then based on whether you see a conflict or not, we'll either let the transaction commit or we'll let it abort. Okay? Now what we do, how we timestamp read and write, we'll come back to next time. We'll stop here. Okay? But the basic idea is we will use Lamport's clocks to do this. We are not going to use physical timestamp, okay? Because this is a distributed system. So we assume clocks are not synchronized or cannot be synchronized precisely. So you still want to be able to reason about events. And we use Lamport's clocks to do that.